Thank you for joining our Open-NFP summer webinar series. Joining us today is David George, lead engineer from Netronome, who will present on the topic P4-based VNF and Micro-VNF chaining for servers with intelligent server adapters. We'll be posting the slides, links to the project code and scripts, and the replay of the webinar shortly after we are finished. We'll be happy to take questions throughout the webinar. Please post any questions in the question field and we'll answer accordingly. A little about Open-NFP before I turn it over to David. Open-NFP's objective is to support and grow reusable applied research in data plane network functions processing. We do this by focusing on reducing the barriers to performing research in this space to researchers and developers creating, implementing, and verifying their ideas on production networking hardware. Open-NFP supports research in a wide range of technologies, including software-defined networking, OpenFlow, Open vSwitch, and P4. We support researchers with a variety of tools, including deeply discounted hardware, IDE software, and cloud access to development systems, and direct support from our engineers in the research community. We also provide support to learning advanced networking concepts on our hardware through tutorials and seminars like the one we're having today. We encourage proposals to research funding agencies. We invite you to join the 20+ universities and companies working directly with Open-NFP through projects. Thank you again for attending. Take it away, David.
Thanks very much, Brian. Great, let's get started. Right, so I'm going to be running through the demo I prepared for the P4 workshop this year. And the title is P4-based VNF and Micro-VNF chaining for servers with SmartNICs. So just a quick run through of what to expect in this session. We'll start off with an introduction, and then we'll move on to looking into the design of the demo in a bit of detail. And we'll look under the hood, look at the P4 and the C source and the configurations. The idea here is I want this to be fairly hands-on, digging through the code kind of webinar. So we'll run through the demo, looking at all the key features that I presented. We'll do conclusions and then questions, and then time permitting, as a slight tangent, we'll look at the SDK6 P4 runtime, so how interaction with our P4 solution works. Okay, great. So first of all, what is a VNF? VNF stands for Virtualized Network Function. So that is a network function hosted independent of physical hardware. So typically this will be some kind of network block, software block running on a virtual machine using virtualized I/O. And these can be anything really, any network operation. But for example, it could include a firewall or intrusion protection. So one of the things I tried to address in the demo is how to chain these VNFs together, how to connect multiple virtual machines. So a VNF is fairly well known, but what exactly is a micro-VNF? Well, a micro-VNF is just really a lightweight VNF as you'd expect. And the idea is that it's possible to integrate it closer to the data plane without having virtual machines and that kind of thing. So, for example, it could go in the Linux kernel or your OS kernel, or as we'll show here, it could go on a SmartNIC. So these tend to be kind of small functions, like statistics or telemetry might be examples of these. They can also be kind of offloads for a VNF. So it's that kind of, it just really is just a very small network function. So the main goal is to illustrate how we can achieve these things using the P4 data plane using Netronome's SDK6 on the SmartNIC. So we'll be doing our micro-VNFs in Sandbox C, and we'll choose a very simple. We'll be showing very simple VNFs, which will run on virtual machines using libvirt to control them and VFIO to get the packets in and out. And we'll have a close look at some some kind of neat P4 features that we support. So why this example? Well, the idea is to show how simple a solution we can come up with to solve relatively challenging problems using P4 and SmartNICs. So the marshalling of the data into VNFs and gathering telemetry and all that kind of thing, we come up with something very, very simple which does these things. So just a quick overview of what we're going to see. The demo consists of a single x86 host, and in that x86 host is a Metronome SmartNIC with programmable P4 and C data plane. And hanging off that SmartNIC is a single physical interface that loops back into the same x86 host and into a regular dumb, in inverted commas, NIC. And what we have there is a bridge between two Linux namespaces. And the idea here is we're going to, the namespaces are there to isolate the networks, so we can communicate through the dumb. Sorry about that. Through the dumb NIC into the back through the VNFs and then back through the dumb NIC again. So so that's the physical interface, and then we have the virtualized I/O interfaces, and those go into the VNFs. So we have two VNFs, and they are two L2 bridges done in two ways. One as a Linux NetDev, which is a regular network interface, and the second is a DPDK app. So on the data plane itself, we have really two parts. There is the Micro-VNFs, which do two things: payload scanning and hop time statistics. Now, hop time we define as the time to get out of the data plane into the VNF and then back again. So it's just really how long it takes for the traffic to hop to the VNF and back, and we accumulate stats on that time. So the other thing we have is a separate path with TCP metering, and that's really just to show how easy it is to do things like metering with P4. Right. So our P4 data plane isn't particularly fancy. This is just a demo. It's not really a full application. So there's run-of-the-mill parse, match, action, and forwarding. Just to repeat this, we have L2 forwarding cooked two ways on the VNFs. So we have virtual machines running a DPDK bridge and a regular Linux net bridge on NetDevs. And this is chosen just as the simplest application we can do in a VNF. But as it turns out, L2 forwarding is a little bit complicated because you have to make sure that from traffic from the two different namespaces take two different paths through the VNFs. So we'll have a closer look at that later. On the micro-VNF side, we've got, as I said, VNF hop time statistics. So we'll be getting the minimum, the maximum, and the average latencies reported through the VFs to send and receive. And the way we do this is we introduce a custom tunnel and a custom header called hop time. We'll have a look at that when we glance through the code. And then the other VNF is a simple payload scanner. So this is searching for a compile time token in the payload. And this is interesting in the P4 sense because it uses access beyond the parsed headers. So this isn't something that is possible in vanilla P4, but we achieve this through the use of these C sandbox functions. And as I mentioned, extra point of interest will show you how P4 meters work. And from a traffic generation point of view, we have two VLAN IDs that dictate the routing between the VFs. And this is so we use the VLAN ID to choose the direction it hops between the virtual functions. And we use Linux network namespaces to address the address spaces. And this is purely done because this all happens on one host. So we need a way to send traffic, force traffic to go all the way through all those hops and back without without going directly to the other namespace. And Linux namespaces are just a way to essentially isolate network stacks from each other running on the same host. Right, so you'll apologize for the slightly wonky lines here, but this is the general idea. We've got traffic coming from, in this case, a namespace with VLAN 3 attached to it. It hops through the micro-VNFs. We chain the two VNFs, and we come back and we land up going through the other namespace on VLAN 2. Right, so just a very coarse look at what the P4 does. In parsing, we parse Ethernet and VLAN, and our custom hop time header. We parse IP and TCP, so we can do the TCP metering. On Ingress, if a hop time header is detected, we remove that header and we process the statistics at that point. We do TCP metering in the Ingress, and we do forwarding. So basically, deciding which port to send the traffic out on. On Egress, we insert the hop time header, conditionally based on what the egress port is, and we translate the VLAN tags. So we, remember that picture, we go from VLAN 2 to 3 and 3 to 2. Okay, so at this point, let's just have a look at the source. Right. So what you see here is Programmer Studio, and on the left we have the parse graph. You see that's generated from the P4. In this pane we have the P4 source code, and you might notice we are already running. So this code has been built and been loaded onto the SmartNIC and is currently running. So it's accepting traffic. Right. So these graphs are kind of nifty, because when you click on start, it jumps the cursor to start. For example, if you jump to parse IPv4, you'll see it jumps to IPv4. So it's kind of it's a very nice way of navigating a simple application like this. So we parse Ethernet, we parse VLAN, and then we parse our custom hop time header if it's present. And we do that via a, if we jump up to the top, we'll see we've defined a special ether type for the hop time header. And here we have the hop time definition. It's super simple. All it is time and an ether type, so we can chain the headers together. Right, and we parse again IPv4 and TCP just so we can do the metering. From an Ingress point of view, things look a little bit more complicated, but really it's quite simple. We've got two processes essentially. We process the hop time if hop time is valid, so that means if the hop time header is present, we process the hop time for either tagged and VLAN tagged and untagged cases, and then if TCP is valid, we apply the TCP throttle. Otherwise, we do forwarding for both cases, the tagged and untagged. So if we click on these nodes, we'll jump to the table definition. So that process hop time ETH is a table, or let's look at the VLAN rather, because that's the case we're interested in. Process hop time VLAN, and there you can see the allowed actions, and that action is defined there. So this is the set of actions that will be done when this condition is met. And you'll see here we call a function hop time statistics. So that hop time statistics, if we jump up a bit, where is it? Is defined as a primitive action. So that's an external action that we're going to define in C. So just a bit later we'll have a look at the C source. Let's just jump back here. And then we modify the ether type, the outer ether type, and then we remove the hop time header. So we always remove the hop time header whenever we detect it. Right. So let's have a look at the TCP throttle. It's kind of interesting. There's the TCP throttle case, and you'll note that we actually aren't doing any matching in that table. We just have a default action. So this is going to throttle any TCP traffic at all. So if TCP is valid, then we do the TCP throttle. We could, in theory, put any matches here we wanted. We could say, for example, we could do it on TCP destination port or source port, or the options are kind of endless. But that's what we've decided. Just a single meter for all the TCP traffic. So here is the meter definition. And you'll see we've only declared a single meter. In P4 you can declare a large array. You can also have 1 meter per rule for the table. And here we have a pragma. So this is specifically for our P4 implementation. We have this pragma to automatically drop traffic if the meter color is red. And this is a workaround for complications introduced due to our architecture of caching lookups. But this is documented in the release notes. So here is the action. We execute meter, and we pass this meter color along with that, and then we modify the field egress spec. So that is telling the P4 program where to send the traffic, and that comes from this rule. That'll come from the rule. Okay, great. So that covers ingress. So very simple. Process hop time, do the TCP throttling, and then I nearly forgot forwarding. So the forwarding, what that does is, again, it sets this egress spec, standard method egress spec, and that's the standard way of telling the packet where it's going to go. And then we do this payload scan, and this payload scan is another one of these custom primitives. Or let's jump to it again. Primitive action there. There it is, payload scan. Great. So this is another thing we've defined in C code. Right. On egress, it's a bit simpler. All we do really is manipulate the VLAN tags. So this is going to translate the 2 to 3 and 3 to 2 for the routing between the VNFs, and also so we get traffic on both ends of the namespace. And then we have insert hop time. So this insert hop time will be conditionally done based on the egress port, so where the traffic is going. And all it does is it adds the header hop time and links it in with the ether type. And what is interesting to people who might have done this before, it just does a simple modify field for the timestamp. So if we have a closer look at this intrinsic metadata timestamp, let's go to the definition up top here. Here it is. So this is a magic header definition that will, if you instantiate intrinsic metadata with this field, that field will automatically get populated with the time just immediately before parsing. So this allows us to do timestamps without the use of external C calls, which it's generally, if you look through our examples, that's generally how it's done. So this is an option for getting the time. Okay, great. I think that covers the P4. So let's have a closer look at the C source. So remember, there are really only two functions. The first is the payload scan. So what we do, you'll have to, the sandbox C is slight. It might look slightly unfamiliar to people, and there is a great reference. It's the joy of micro C. I think Nick mentioned it in his webinar. And once when I commit the code, I'll do what Nick did, and I'll have a link to the document up at the top. But anyway, so in this code we define a needle which we're going to search for, and in this case it's BOOM, all lowercase. And here we define a variable for the number of detections. So interestingly, this export token kind of means that variable will be shared between the data plane code and the host code. So when I go through the demo, I'll show you this. We can very easily access this variable from the host. Right. And so this is the code which does the payload scan. It is kind of complicated in that the way our chip architecture works is that for large packets, they can be split into two memories, and there's a close memory called the CTM, the cluster target memory, and there's external memory, which is, I guess, more akin to DRAM. And the idea is that the close memory has much lower latency than the external memory. So if we want to scan through the whole payload, we sadly have to go through the close memory and the far memory. So that's what we're doing here. We're picking up in this mu length variable, we're picking up the amount of data that is in the external memory unit. So for the scan, we get a pointer to the payload, and that is the payload after the parsed headers, and we figure out how much data there is to scan. So we run through until we run through all the data at that pointer. We do a memory read, and the way IOs work is that the data gets transferred to or from transfer registers. So this payload data, if we look up a bit, we'll see it's an X read, a read transfer register. So what we do is we copy data into there, and then we copy it into a different memory type. And this is because transfer registers have certain limitations. You can't iterate over them. So we transfer it into a memory we can iterate over, and then we just we scan for that token, and we keep track of the progress, and we update it. And if the progress is the same as the size of the search token, we increment the detections variable. So we'll be able to pick up that value from the host. If the needle is detected, we drop the traffic. Okay. So then what we do is we do the same thing, but for the external memory. So the code is very much the same. We get a pointer to the payload, we iterate through it, and we search for the token, and we accumulate the stats, and we drop it. If the token isn't found, we return forward. So this indicates the data plane must continue processing, and this indicates the data plane should stop processing and drop the packet. Just want to see if there's a question here. Oh, okay, that wasn't a question. Wait, let's see here. Oh, okay. Okay, there are a bunch of questions here. Okay, I'm just running through them here. What is P4? Okay, we'll get to those later. Bapi must just interrupt me if there's something that I should answer right now. Okay, sorry about that. Let's keep going. Okay, so that's the payload scanner. Just simply scanning for a token and dropping if it's found. Okay, the hop time statistics. What we're doing here is we're gathering a bunch of data per ingress port. So we get what the max latency is, the min latency. This is the number of packets that we've seen, and this is an accumulation of the total latency. So what we do is we grab the current time from the metadata timestamp. So we have access to all the parsed headers and all the P4 metadata from the C sandbox. So what this is doing is it's accessing that and loading it into a C variable. And then here we're grabbing the ingress port, same process from the P4 data plane. Here we are grabbing the time as represented in the header, and then we get the latency, which is the difference in the time. So at this point we know how long it took for the packet to leave the data plane and arrive back again. So what we do is we grab the old version, we do an IO, remember the transfer registers, we copy it into normal registers, and then we do some simple, it's very simple, just check if it's bigger, check if it's smaller, and then accumulate, and then write it back. And that's all it is. And that's pretty much what the data plan does. So if we look at the configuration here, so this is the rules editor. Let me just get rid of the graphs. So the configuration editor is a place where we can load up configure tables and meters and whatever else we need to. So if we look at some of the interesting, I won't go through all of them. So here we have the TCP throttle rule, and you can see it just does TCP throttle on P0. Let's see what else is there. Manipulate VLAN. So we have two rules here that just translates the VLAN from between 2 and 3. From 2 to 3 and from 3 to 2. Process hop time. Where is it? Forward VLAN. Okay. So this is the actual routing between all the VFs. So if here we do a match on ingress port, we do a match on VLAN 2. So in this case, we're directing traffic coming in from the physical port 0 on VLAN 2 to the VFIO port 0. And then we do roughly the same thing. So when it comes back on VFIO 1, we send it to VFIO 2, and then from VFIO 3, when it comes out of the second VF, we send it to physical 0. So we just send it back. And then this is the same thing pretty much in reverse from using VLAN 3. Right. So at this point, we are ready to interact with the thing. So let's minimize all of this. And here we go. So what you see here are these are shells on the host, and these are basically scripts to interact with the design. And this will all eventually all be on GitHub. So if I run demo setup just like that, it's going to shut down the virtual machines, and it's going to bring them up again and set up all the namespace stuff. And at that point it'll be ready to test. Okay, I've provided no arguments on that. So what's going to happen now is both VNFs are going to be set up to be NetDev VNFs. So let me, on this screen, I will just clean up the hop times because all the L2 stuff would have polluted them a bit. And then I'll set up, there we go, set up a watch on the hop times. So this is going to update when we see traffic. So there we go, demo ping. So this is going to ping between one namespace and the other. There we go. I'm going to clear the stats again because there was a long delay initially. I'm not sure why. Okay, so here we go. So this is measuring the time it takes to go to the VNF, the NetDev bridge, and back. You can see there's an interesting variation. But largely they're sitting at around, let's say, 180 microseconds. Right, so let's just stop that. I'll just run it once, so we just have it on record. So what I'll do now is I'm going to restart all the VMs, but I'm going to set the one VM up, the VNF 0. I'm going to set it up for DPDK, and that second parameter is a mask for the VMs. So if we just wait for that to come up, 1 second. moment. Okay. DBDK. So what I've done on the right terminal here is I've started the DBDK L2 forwarding app on the virtual machine. So now when we ping, we should see, I'm just going to increase the interval, or decrease it rather. It's going to ping a bit faster. And we watch the hop stats. Let me just clear them because they get diluted by all the initial stuff. So here we go. You'll notice there's a distinct drop in the latency, as you'd expect for the DBDK app, to around 100 microseconds. So it's just kind of interesting. You can see the difference between the two. Right. The next thing I wanted to demonstrate was the payload scanner. Remember, it's searching for the letters for the word boom, so I called this the boom filter. Yeah. Okay. So let's have a look at demo payload scan. I'm going to just start up 2 netcat sessions. So netcat is a very simple tool. So the most simple way probably you can transfer data from one side of a connection to another. So we'll start up the listener, and then over here we can start the demo scan, and we'll start the other end of the connection. So here we go. There we go. It gets through with ease. But if we type boom, it doesn't. It gets dropped. So remember I mentioned the needles detection variables. There's a very useful tool that ships with the BSP called NFP RT-SIM, and this will give you all the runtime symbols. So if we go detection, if we just look for the detection symbol, there it is. So this is a bit of memory that will hold the value of the needle detection. So if we go and we do NFP RT-SIM, excuse me, if we do NFP RT-SIM and we paste it, let me do it here where it'll work a bit better. Sorry about that. There we go. We have live. We see 1 out of it. So we can go watch. And these runtime symbols are probably the single most useful thing for debugging and interacting with the SmartNIC in general when you're coding for the SmartNIC, but and also for in the sandbox C case. It's very, very helpful. So we go. Oop, yep. There we go. Detected 2. Remember, lowercase, and that gets through. Right, that's the payload scanner. Kind of neat. Okay. So the final thing I wanted to show was the TCP metering. So if we go back to our Programmer Studio and we look at the configuration editor and we see metering, we click on the meter, and here we go. We've got the meter set up to meter at 88.99 kilopackets per second. So it's kind of P4 meters. You're allowed to do packets per second and bytes per second. So you can control either the packet rate or the bit rate, which is kind of unique. Okay, so let's see if that works. Let's just minimize Programmer Studio and let's have a look at TCP meter. Right. To demo this, we are going to then use netcat, but you could use iperf or whatever you please. We're going to just start something which puts all the data in the background. Just writes it to dev null, and then we are going to traffic through. So, and let's have a look at the TCP Mesa stuff. And here there's a script called watch packet rates. Right. I might not have saved the rules. Let's just try this again. So when you Control S save, it will do a reload. And that will write the rules to, that'll commit the rules to the runtime server, which will affect the behavior. Let's see if that's had an effect. Okay, great. Thank goodness. Okay, so there we have it. So we are now limiting the packet rate to approximately 89, approximately 90, I guess, kilopackets per second. So we can change this to something more interesting. 3.1459. Save that. Control S to save and reload the rules, so that will commit the rules to the SmartNIC. And then if we can minimize Program Studio again, you'll see now it's limiting to around 3.1 kilopackets per second. Okay, I guess that pretty much concludes the demo part. Let's just have a look back at the presentation. Okay. So what are the conclusions? What we've done is we've illustrated a very, very simple solution from scratch to connect VNF together using P4. And we've showed the potential for using for implementing micro VNFs in C sandbox. And specifically, we've done what P4 can't do. We've gone beyond the parsed headers in the C. And we've shown you can do useful things like measuring processing time for VNFs without much difficulty. And generally speaking, we've also showed how P4 meters can be used and how flexible they are. We had it just on if TCP is valid, but you could have it on a specific a meter per TCP port combined with an IP port. The options are endless, and this is I guess what we're showing. We're showing how flexible P4 is and how you can do interesting things, different things, without very much difficulty. Okay, so here's just a link to the GitHub resources. I wanted to get everything up today, but I just haven't had time, so expect that to go live in the next day or so, and we'll have all the P4 source, all the sandbox C, and the P4 configs, as well as how to build from command line and Programmer Studio. So we'll have both methods of building and loading will be there, and all the host scripts you've seen will also be committed. So how to start up all the VMs, issue traffic, and all that kind of thing. Look at the hop times, which is probably the most useful example. Yeah, so the virtual machines themselves won't be committed, but I guess that's largely an exercise for the listener, I suppose. Okay, so official question time. If anyone has anything that they'd like to say. I'm not super familiar with the webinar format, so if one of my colleagues can drive it, I'd be happy for that to happen as well.
We have one question coming in. Just one sec here.
Okay.
Okay. So I guess the question got lost in the queue. So we'll just go ahead and wrap it up now. I'd like to thank David for a great presentation, and I'd like to invite everyone to please register for our 5th in the 6 series webinar. It's coming up August 24th at 8 a.m. Pacific. It's P4, eBPF, and Linux TC offload. And that's going to be coming from a few folks from the software engineering team of Metronome. So please register and join us in 2 weeks, and we'll be happy to talk to you then. Thank you.